We're going to talk about the concept of dimension. I did already mention that dimension is very closely tied up with the notion of basis. We'll see how that plays out in the subsequent slides. All right, before we define dimension, first of all, we distinguish between finite dimensional and infinite dimensional. And we say a vector space is finite dimensional if it has a basis with only finitely many vectors. Okay, here's some examples. R3 has a basis with 3 elements. Quadratic polynomials have a basis with 3 elements. 2x2 matrices have a basis with 4 elements. Notice that we're not saying 3-dimensional, 4-dimensional just yet. We're only distinguishing these as finite dimensional because we know that they are have bases with finitely many members. Later on, we will show, in fact, that each of these spaces has a characteristic dimension, but we're not prepared yet to make that statement. Okay, so from this point on, we will restrict our attention to vector spaces that are finite dimensional. So we're going to assume that we're dealing with finite dimensional vector spaces. Now, when you do analysis or something called functional analysis, then you will be talking about infinite dimensional vector spaces, but that's another task for another day. All right, so we will show that for any finite dimensional space, all of its bases have the same number of elements. Okay, here's an example. Each of these is a basis for P2. You can see that all of the degree 2 polynomials can be written as a linear combination of these 3, or of these 3, or of these 3, or of these 3. And each has 2 elements. Of course, it doesn't have 2 elements. I think that's just to throw you off. Each has 3 elements. And here are 2 different bases for the 2x2 matrices. And these both have 4 elements. Okay. So in order to prove that any 2 bases of a vector space have the same number of vectors, we'll first prove this exchange lemma. Exchange lemma says the following: assume that this B is a basis for a vector space, and that for the vector V, the relationship V expressed in this form has Ci unequal to 0. So we're picking out one particular I and making sure that that coefficient is non-zero. Then, if I exchange Vi with V, then I get a different basis for the space. Okay. In other words, instead of Bi in my basis, I change my basis, I throw out Bi, and I include V instead. Okay. It's a different set of vectors, but this gives me also a basis for the space. Okay, let's look at the proof. Suppose that we exchange Bi for V, and first we want to show that this set is linearly independent. Okay. Now, suppose we have a relationship that involves V. Okay, so we can we would write the relationship this way. Then we substitute in for V, and here we get a relationship for the betas. Okay. All right, now we know that the betas form a basis. So that means all the coefficients of all the beta n's must be 0. Now look at the coefficient in this expression for beta I. Here's the only beta I in the expression. The coefficient of beta I is Ci times Di. Now we know that all the coefficients in this expression are 0 because the basis cannot have a non-trivial linear relation. So that tells me that DICI, which is the coefficient of BI, must in fact be 0. But at the beginning we assumed that CI was not 0. That means DI must be equal to 0. Okay, so we've shown that in this linear relationship with a V, we must have this coefficient di, this coefficient must be 0. Okay. But what about the rest of these terms? The rest of these terms is simply a linear relation among the beta i's, except for among the different betas, except for beta I. That means that all these other coefficients of betas must be 0 as well. Okay, so in this way we've shown that in fact every coefficient in this expression must be 0. All of the d's must be 0. And that means that there is no linear relation among these vectors. Okay, so these vectors are linearly independent. If I exchange bi for v, I still end up with a linearly independent set of vectors. Now we finish the argument by showing that this new set of vectors with bi replaced with v has the same span as the original b that includes bi. Okay. Half of this argument that b hat is contained in b is easy. We can write any member in b hat as this linear combination, simply substituting the expression for v in terms of b. And this is a linear combination of the members of b, which means that this vector in b hat must also be in b. That shows me that b hat must be contained in b because every element of b hat is contained in b. For the other half of the argument, recall that if v is a linear combination of the betas, where ci is not 0, then we can rearrange the equation to get beta I as a linear combination of beta 1 up through beta n and v instead of beta I. So in other words, I can get beta I as a linear combination of the vectors in beta hat. Okay. All right. And then we can use the same argument. Since I can get beta I as a linear combination of the vectors in beta hat, and certainly all the other betas are linear combinations of the vectors in beta hat, that means that I can get any vector in B, in the span of B, as a linear combination of the vectors in beta hat. Okay, so I can prove the inclusion both ways. Beta hat and beta have the same span. If I replace beta I with V, I have the same span. I still have, if I start out with a basis, I'm still going to have a basis. Okay. Okay. We can use this to show that all of the bases of a space have the same number of vectors. Okay. That's what this theorem says. In any finite dimensional vector space, all bases have the same number of elements. Proof is as follows. Fix a vector space with at least one finite basis. Okay, choose one of these bases, or we call it with the betas, and choose one that is the smallest size. Okay, we will have at least one of smallest size because you can't have a basis with less than 0 vectors, so there must be one of smallest size. We will show that any other basis D also has the same number of members n. Because B has minimal size, D has no fewer than n vectors. We will argue it cannot have more than n vectors. Okay, so in other words, B is the smallest possible basis, or one of the smallest possible bases. D is any other basis. And we know that the number of vectors in D must be bigger than or equal to the number of vectors in B because B is of minimal size. So we want to show also that that the number of vectors in D must also be less than or equal to the number of vectors in B. And that will give us that the number of vectors in D is equal to the number of vectors in B. So that's our strategy. Okay. So we want to show that D has no more vectors in it than B does. No, the basis B spans the space, and delta 1 is in the space. So delta 1 is a combination of the elements of B, and it's a non-trivial combination. By the exchange lemma, we can swap delta 1 with a vector from B, resulting in a basis B1, where one element is delta 1, and all the other n-1 other elements are betas. Okay, so I started out with beta 1 up to beta n. I showed that I can take one of these betas. I'm not sure which one, but I can swap at least one. I can replace that with delta 1. Okay, now you can see what's going to happen here. We're going to replace these vectors one by one, and eventually we'll show that we still have a basis with the deltas. Okay. The prior paragraph forms the basis step for an induction. The induction step starts with a basis beta k, containing k members of D and n minus k members of B. We know that D has at least n members, so there is a delta k plus 1, okay, because here k is less than n. Okay. So that means that k plus 1 is less than or equal to n. I can represent this delta k plus 1 as a linear combination of the elements of bk. Now let me write down bk to make this a little bit more clear. What is bk? What is bk? Bk is a basis. It has some betas. I'll just write it this way. It has some betas. It has some deltas. Okay. Okay. Something like that. I'm not going to be specific. It has n vectors in it altogether. But we know that there are k instances of delta. Okay, so that means I have delta 1 all the way up to delta k. Now I can write delta k plus 1 is in the span of beta k. Okay. However, delta k plus 1 is not in the span of delta 1 through delta k. Why is that? Because we know that deltas are a linearly independent set. So that's the key point that is mentioned here. In the representation of delta k plus 1, at least one of the coefficients of one of the betas must be non-zero. Otherwise, I would have a linear relationship among the elements of delta. As soon as I have a non-zero coefficient of one of the betas here, I can replace this beta with delta k plus 1 by the exchange lemma. Okay, so what I have now is a basis with k plus 1 deltas and one fewer of the betas. In this way, I can replace all of the betas one by one with deltas. However, I never change the number of vectors. I'm always replacing a beta with a delta. I'm never adding or subtracting to the total number of vectors. So by the end of this process, when I take beta n, I'm going to have vectors, all of which are deltas. They may be in a different order. I'll just write the delta m, delta q, but they'll all be deltas. And this is a basis. Okay, this will be a basis. So let me go to the words here. That's exactly what this says, that after we continue on the nth step, we're going to have all of these deltas in some order. Now, D can't have more than these n vectors, because if it did, any additional delta would be in the span of these n vectors. Okay? But that's not possible, because we know that the deltas are linearly independent. In some sense, they're a minimal spanning set. So it's not possible to have any deltas left over at the end of this process. Okay? So we started out with betas, we replaced them with deltas, we still have a basis. That means that the set of deltas must have n elements. Okay? So that shows, since delta was arbitrary, that means that any basis delta, like just see delta m, has the same number of vectors as this minimal basis. Okay. So that means that any basis in this particular basic vector space will have the same number of vectors in it. Okay. So this gives us a definition of dimension. The dimension of a vector space is the number of vectors in any of its bases. Doesn't matter which basis I choose, they'll all have the same number of vectors. All right, for example, the vector space Rn has dimension n because that's how many vectors there are in the standard basis. Somehow I messed up here. Go back here. All right, so here we have another example. Three-dimensional vector space, n plus one dimensional vector space. You can read through these examples. They're pretty natural. Okay, here's another example that comes from a system of equations. I can take the solution set of this system is a vector space. We can check, we did some exercises where we did check such systems, solutions have the property that they're a subspace. Okay. If we solve the system and parameterize, we have two vectors as a basis. Okay. I won't go through the steps, you can do the algebra. So these two vectors that parameterize the solution space form a basis. So this is a vector space of dimension 2. Right. Now notice here that we have R4. Okay. And when we reduced it, we had two linearly independent conditions. So 4 minus 2, we ended up with a basis of 2 elements. So that's going to be true in general. Okay, corollary, no linearly independent set can have a size greater than the dimension of the enclosing space. Okay, if I take a, all right, so let's see the proof. The proof of Theorem 2.5 never uses that D spans the space, only that it's linearly independent. So in the proof of Theorem 2.5, we showed that D could not be larger than the number of vectors in the given basis B. So the corollary follows from the proof of the previous theorem. Another corollary, any linearly independent set can be expanded to make a basis. Here's the proof. If a linearly independent set is not already a basis, then it must not span the space. Add to the set a vector that is not in the span, and that will preserve linear independence. Okay, you can go back to this lemma and read that proof. Okay. So you can keep adding vector after vector by this process, by finding a vector that's not in the span, until we find a set that does span the space. And the corollary here says that that process must end before the number of linear independent vectors is equal to the number of vectors in the basis. Okay, so we can just keep adding vectors. There's a limit to the number of vectors we can add. We already know that. So at the end of this process, we must end up with a basis. We can also shrink spanning sets to get a basis. We just showed that we can expand linearly independent sets to get a basis. Now we're showing that we can shrink spanning sets to get a basis. All right, the proof of this corollary, let's call the spanning set S. If S is empty, it's already a basis because the only space it spans is the trivial space, so it is a basis of the trivial space. If S is simply the single vector 0, then we can simply remove it and get the empty basis of the trivial set. Often we don't worry about this trivial case. Usually we just assume that S is a non-empty set that also has non-zero vector. So let's begin with that case. If neither of these trivial conditions are true, S must contain a non-zero vector, and we can form a basis B1, which consists of the single vector S1. Now notice that this basis B1 is not necessarily a basis for the span of S. If it is, then we're done because this basis is a basis of the span of S. If not, then we can find another S in the span of S, which is not in B1, in the span of B1, sorry. So we add to the set B1 this additional vector, and by this lemma, this set is linearly independent. So why is it linearly independent? The lemma says that if I have a linearly independent set and I add another vector which is not in the span of that linearly independent set, then the result is also linearly independent. So in other words, we know that this set is linearly independent, and this has a larger span than the original span of B1. Okay. So it's possible that the span of B2 is the span of the entire set S. If not, we just continue. We continue throwing in vectors that are not in the span. Every time we throw in another vector that's not in the span, we can guarantee that we still have a linearly independent set. Now, this process can't go on forever because otherwise, then we'd have a set of linearly independent vectors that was infinite. And we know that we're in a finite dimensional vector space. Okay, so this process must end at a certain point. Once it ends, then we do have a set B, which is a basis, whose span is the span of the same as the span of S. Okay. So in summary, we can shrink set of spanning set to get a basis, and we can augment a linearly independent set to get a basis. So you could say a basis is a minimal spanning set, and it's a maximal linear independent set. All right, in an n-dimensional space, a set composed of n vectors is linearly independent if and only if it spans the space. Okay, first we will show that a subset with n vectors is linearly independent if and only if it's a basis. Okay. All right, if is trivially true, bases are linearly independent, okay? Only if holds because a linearly independent set can be expanded to a basis, but a basis has n elements, so we can't add any more vectors to the set we've already started with. To finish, we'll show that any subset with n vectors spans the space if and only if it's a basis. Now, certainly, if it's a basis, then that subset spans the space. Only if holds because any spanning set can be shrunk to a basis, but a basis has n elements, and this shrunken set is just the one we started with. We can't throw out any vectors and still have a spanning set. Okay, so we have that the equivalence of n linearly independent vectors in an n-dimensional vector space. We know that it must be a basis. Okay, and we'll stop here.